You'll recall that there are three laws we say that all forces in the universe have to obey. And these are called Newton's laws of motion, named after Sir Isaac Newton, who did a whole bunch of work in physics and mathematics too. And he has a number of laws that we'll talk about in this course. But for now, we're focusing on these first three, called Newton's laws of motion, which are the laws that forces have to obey. Now, Newton's first law, you'll recall, told us that if no net force acts on an object, and otherwise there can be forces on the object, but as long as they're all balanced, they all cancel out, then its acceleration is zero. So if we extend our thinking past that a little bit, you might say it's fair to assume that if there is a net force, in other words, an unbalanced force or a resultant force, then the acceleration of the object would be not zero. And that indeed is exactly true. But what Newton's second law does is it tells us exactly how to calculate that acceleration. So before this video, you knew that if there was a net force on an object, it would have an acceleration. In this video, we tell you how to figure out what that acceleration is. And this leads us to a really, really important equation in physics. I often ask people what the most popular equation in physics is, and people tend to say E equals mc squared, and I probably agree with that. While that's maybe the most popular equation in physics, probably the most important one, you could argue, would be this equation I'm about to show you right here. So this equation is often referred to as F equals ma. I had a professor in an engineering course I was taking at university, and he said that to be an engineer, it really all boils down to knowing two things. First is F equals ma, and the second is you can't push a rope. So that really highlights how important, how fundamental this equation is to physics. So I want to take some time here to unpack this equation. The first thing you might notice here is this funky symbol right at the beginning. Now this is a Greek letter. It's the Greek letter called sigma. And we often use it in physics and in mathematics. And it means the sum of. So sum being adding a bunch of stuff together. What are we adding together in this case? It's forces. So what this whole first part of this equation is saying is if you look at all of the forces acting on an object and you sum them up, you take the sum of those forces, you add the forces together, you'll get a number. And that'll be this whole thing over here. And that number is called the net force or the resultant force. So that's the left side of this equation. We have a bunch of forces acting on an object, whatever they are. We add them all together, and that gives us one number. And we call that the net force. The second side of this equation is a little more straightforward. M stands for mass, and A, you'll recognize, stands for acceleration. So all in all, this equation tells us that if you add up all the forces acting on an object, you get the net force. And that number for the net force is equal to the number you'd get if you take the object's mass and multiply it by the object's acceleration. Before this equation came along, that was not obvious at all. You'd think the acceleration of a mass and the forces acting on it could be totally unrelated. But in fact, they're very, very closely linked. The other thing I'm going to point out about this equation before we move on is units. It's always important to think about. So forces, as always, in the metric system are measured in units of newtons, the symbol for which is just a capital N. The mass of the object, we're going to measure in kilograms, our metric base unit for mass. And the acceleration of the object, we're going to measure in units of meters per second squared, which is our metric base unit for acceleration. So these meters per second squared, kilograms, newtons are all units you've heard about before. And this is them just packaged together into one equation. So there you have it. F equals ma. The sum of all the forces acting on the object is equal to the object's mass multiplied by its acceleration. So one thing that I think is worth noting is what happens if we take a look at the units on both sides of this equation. So as I just pointed out, on the left here we have newtons, on the right we have kilograms and meters per second squared. One thing I like to sort of drive into the heads of my students is that we're very used to using equations with numbers, right? If I gave you a number for the net force, you could put it in here. If I gave you a number for the mass, you could put it in here. We can also do that with units. So instead of subbing in a number for the force and a number for the mass and a number for the acceleration, we could sub in the units for force and the units for mass and the units for acceleration. So if I do that down here, I get something like this. The units for force are newtons, the units for mass are kilograms, and the units for acceleration are meters per second squared. But when I write it like this, this sort of illuminates something. It tells me that a newton, the unit of a newton, is equal to units of kilograms multiplied by units of meters per second squared. And often, you might hear people not actually use the term newton, and they'll talk about something that has a unit of kilogram meters per second squared. That's how you pronounce this. So a newton really is not a brand new unit that didn't exist before. It existed, and we called it a kilogram meter per second squared, which is a bit of a mouthful. And so when Isaac Newton did his popular and important work on the subject, we said, you know what? This existing unit, a kilogram meter per second squared that he was working with so much, that's a bit of a mouthful. Why don't we just come up with a nickname for that? And in his honor, we'll call it the newton. So a newton is the same thing as a kilogram meter per second squared. So let's use this in a really, really simple example. We have a 650 kilogram car, and it's accelerating down the road at 4 meters per second squared south. What is the net force acting on the car? So first of all, let's pull out our new equation. And there's a good reason to think that this equation would be useful, right? I'm given a mass. I'm given an acceleration. I'm asked for a net force. Hey, that equation we just learned has all three of those in it. So F equals ma. Let's start by plugging in what we know. Well, I know the mass is 650. There it is. This is in metric base units, kilograms, so I can plug it straight in. I know my acceleration is 4 meters per second squared south. Again, that's metric base units, which is great, so I can plug it straight in. And to encode this direction, I'm going to put a negative sign. We generally say north is positive, south is negative. So since this 4 is south, I'm going to put it down as negative 4. Then we're left with a little bit of simple math here. 650 times negative 4, that gives me negative 2600. We know that because we put metric base units into our equation, whatever we get out is also going to be in metric base units. So because I use the metric base unit for mass and the metric base unit for acceleration, what I'm going to get out has the metric base unit of force. So this 2600 is going to be in newtons. And I get a negative number. Now, these negatives are great to use when we're plugging things into a calculator, but when we're actually displaying an answer or talking to each other, it's nice to be a little bit more specific about what that negative means. And in this case, you'll remember that negative meant south. So my final answer I would write down is 2600 newtons south. Let's look at a slightly more complicated question now. So here I have a little diagram, kind of like the diagrams we were looking at when we did Newton's first law. We have an object here, looks kind of like a boring box. And there are a number of different forces acting on it. There's a force going up, there's a force going down, there's a force going to the right, and there's a force going left. And we're being asked to determine the magnitude and direction of the net force on the object below. So you'll recall perhaps that the net force is what we get when we add all the forces together and let some of them maybe cancel out. First of all, you might be looking at this and wondering, okay, what are these symbols here? What's Fn? What's Fap? What's Fg? What's Ff? That's actually not important for this question. I'll tell you that Fn is called the normal force. FAP stands for applied force. Fg is the gravitational force, and FF is the friction force. We'll discuss those forces in detail more later, and you'll start to use these symbols yourselves. But for now, all we need to know is there's a force going up that's 600, there's a force going down that's 600, there's a force going to the right that's 250, and a force going to the left that's 75. Now, for a lot of you, you can maybe even just look at this question and figure out the answer in a couple of seconds in your head. And that's great. I use a simple example here with simple numbers so that you would be able to do that if you want. But what I want to do is look at the process we would use if we can't do it quickly in our head to solve a question like this. And even if you can do this quickly in your head, understanding this process I'm going to go over is important so that when you get to a harder question you can't do in your head, you know a process that will work. And actually, I'm going to show you two different processes, two different ways you can think about solving this question. And both of them, in effect, are doing the same thing. They're just different ways of thinking about it. So to recap, what I'm wanting to do here is find the net force. I have a bunch of individual forces. I want to add them together and find the net force. So first of all, I'm going to show you a graphical method or a visual way of doing this. And it looks like this. So the goal here is to get the net force, or the sum of the forces, meaning I have to take those forces and add them together. So all I've done is I've taken my forces from up here, 600 up, 250 right, 600 down, 75 left, and I've added them. 600 up, 250 right, 600 down, 75 left. You might remember that the rules for adding vectors are we can put them in any order we want, right? I chose to do this one, then this one, then this one, then this one. But if you did them in a different order, that would be totally fine. Also, another rule for adding vectors is that we add them head to tail. We often say like elephants walk in the jungle. So in this diagram, all the vectors had their tails at the same place and their heads were all out in different directions. But when I actually add them, I rearrange them so they're head to tail, head to tail, head to tail. So here I have two vectors being added, two vectors being added, and two vectors being added. Third thing to remember about adding vectors is that the answer we get is called the resultant, and it goes from start to finish. So I started over here, I'm finishing over here, so my resultant should look like that. And the reason I get this number 175 is you can see, well, I went 600 up and then 600 down, so those kind of cancel out. I went 250 to the right and then 75 back the other direction. So 250 minus 75 should give me the length of this gap, and that's 175. So by just kind of looking at the vectors graphically like that, we can see that the resultant, or the net force, is 175 newtons. So I would probably write that down as my final answer, something like this. The net force, or resultant force, is 175 newtons, right. The other way to think about this is not visually, right? Without thinking about, let's add these vectors together, head to tail, let's draw this square and see which way they're all pointing. Some people just like to work with numbers. So we can do that too. And you'll recall from previous parts in this course that there's a lot of situations in physics where we want to look at what's going on in the x-axis and the y-axis separately, the horizontal and the vertical. We're going to do that here too. So starting with the horizontal, this means I'm just looking at my vectors up here that are horizontal, left, right. So I'm looking at this guy that's 250 and this guy that's 75. These vertical ones in the y direction, we'll worry about those later. We'll worry about those over here. So in the horizontal direction, what am I wanting to do here? That's right, I'm wanting to find the net force, or I'm wanting to add the forces together. So if I take all my horizontal forces and I write them down, I get this. I have a 250 and I have a negative 75. Right? Here's my 250. Here's my negative 75, or my 75 left. What do I do with the 250 and the negative 75? I'm adding them together. And what do I get if I punch that into a calculator? I get positive 175 newtons. So that's what's happening in the x direction when I add all my x vectors together. How about the y direction? Well, you'll recall that in the y direction, we've got a 600 newtons up and a 600 newtons down. So I want to take those forces. I want to sum them up. I want to add them together. And if I do that, I get this. There's my 600 up, or positive 600. There's my 600 down, or negative 600. And I'm adding them together, right? I'm summing the forces. 600 plus negative 600 gives me 0. So what this has told me is that if I want to look at the x and y separately, I see in my x direction, my net force is 175 newtons. And in my y direction, I have no net force at all. So overall, there's nothing going on in the y direction. It's just the x direction I have to worry about, and my net force is 175 positive, or because I'm working in the x direction, 175 to the right. So here's my answer. The net force, or the resultant force, is 175